Okay, phase 6, the brief. So as the project draws to a close and we are starting to look around at other game development studios because we know we're going to ship this product and they're going to fire all of us. No, I did not say that. As we're doing the last bits of polish, our producer has come to us and said, can we create a system to transition between scenes? Now that we have our player, she can walk around, she can pick things up, she can interact with everything in the game. But we now need to be able to go from one scene to the next. And it's important that we also maintain information from one scene to the next. We want to create a system that transitions between the scenes, and we want it to fade to black during the scene transitions. We also would like to have a system that has multiple spawn points, which will be needed due to the multiple possible entry points. I mean, right now we only have 2. We've got between the security room indoors and the market outdoors. But as we expand the game, perhaps she can go into one of the doors outside of the market. And when she comes back in, we don't want to end up by the security room. So we need to have multiple spawn points supported. Create a system to save data between scene loads and unloads. Upon unloading a scene, information such as the position of a game object must be stored so that on returning to the scene, the information can be used again. So the typical example is the coin. We pick up the coin. We don't want to return to the scene and find out that there's another coin still in that vending machine. We've come up with an approach, and the project architecture is going to be based on a main or persistent scene that will stay loaded at all times. That persistent scene will handle the loading and unloading of other scenes. Certain information that needs to persist through all scenes, such as the inventory, can be stored in the persistent scene. However, the persistent scene is not suitable for all stored information, such as the details of that game object that exist only in one particular scene. It's not a great place to store, where is the coin in the persistent scene. So the scriptable object assets will be used to temporarily store data so that it can be loaded again when we return to the scene. So scene controller architecture. We can see what it shows on screen and what's loaded into memory. But essentially, we're going to fade to black. Then we're going to take scene 1 and we're going to unload it. Then we're going to load in scene 2, still while we're faded to black. And then we will fade and show our scene 2. Now our save data architecture. So we have our scene. It has things that can change. In this case, sort of 9 abstract rectangles that can change. And then when we play the scene, we change a number of different things. It could be the location of the player, the location of the bird. And then we want to save the relevant data. We're not going to save everything, just the relevant data into an asset so that when we come back to that scene, it's always going to load from its default state. We're going to have everything the way it was when we left it as a design in our design phase. And so then we need to find a way to reload that change from that asset. And specifically, let's say we have our market. And the thing that we want to save is the coin. And we will use a game object activity saver script to save that in a scriptable object called market save data. And it will save the state of the coin game object. Now, I think it's important to note that when we're talking about using scriptable objects to save data, that they are temporary and they are runtime only. That these are not acceptable places to store data between sessions. And this has to do with, primarily actually, with security and platform architecture, which is that the location that scriptable objects reside in your project, if you were to save information to it, you'd be saving information on your build to files in the runtime. And you would get your operating system constantly telling you, hey, something's trying to write to your your executable package. You know, do you want to approve this? I needed the administrator to approve saving this. So part of the reason that we aren't saving permanent data like a saved game to scriptable objects is just due to the nature and architecture of platforms in the games that we're building. And so we're going to talk in this section quite a bit about delegates, events, and Lambda expressions.
So what we're used to storing is data. We're used to storing a bool that holds true or false, a string that holds some words. But what we can do is we can create variables called delegates, and they store functions. So we've got a type that we're going to be using quite a lot, which is called action. Now, an action is a specific type of delegate that represents a function that has no return type and no parameters. You can store a function as a delegate as follows. So action is the type of delegate that we're using here. We're calling our action variable myAction, and we're storing the function. So important thing to note here is that it's stored by not using the parentheses. It's called a function group when you do that. Once it's stored as part of your delegate, you can call the functions that are stored in there using the name of the delegate followed by the parentheses. Actions also come in generic types. You can have many different types of generics with actions, but the example that we're using here is an integer action. And in that case, when you give it a generic type, it represents a function which returns nothing, but takes an integer of the types that you're giving it generically. So an integer action represents a function which returns nothing and takes a single integer parameter. The main reason that we have delegates, the main thing that we get out of them is that unlike functions, you can pass a delegate to a function like a parameter. So say, for example, you've got a very long, very slow function, and you only want to call it if it's really necessary. You don't want to pass that as a function and have it called, because then whenever the function that you're passing it to is called, you're going to get that long function call. Instead, you pass it through a delegate, and then your parent function decides whether or not it's going to call the delegate function. You can subscribe to and unsubscribe to a delegate using the plus equals operator or the minus equals operator. So this means that you can add multiple functions to a delegate at once, and that would result in multiple functions being called when you call the delegate. So now we're going to talk about events. Now, I want to be very clear here. We're not talking about the same events that we've been talking about before. This is not Unity's event system. This is C# events. Now, C# events are particular types of delegates. We make a delegate an event by adding the keyword event before its declaration. So here we've got public event action, my event action. With events, it's very, very important that once you have subscribed to it, you definitely need to unsubscribe to it. And the reason for that if the event is subscribed to, then it stores a reference to that subscription. If it's never unsubscribed, then it maintains that reference. So that means it never gets garbage collected and you end up with memory leaks. So this is very, very bad. The most common way that we deal with subscribing and unsubscribing, the best way that I can recommend to you is you subscribe in onEnable and you unsubscribe in onDisable, because we know that those functions are always called in pairs. If you get onEnable, it means you're definitely going to get an onDisable, so you subscribe and you're definitely going to get an unsubscription. If you're getting an onDisable call, it means you've definitely had an onEnable call. Calling events works exactly the same as calling delegates. They're very, very similar. They have some very subtle differences which we're not going to go into here. So once you've subscribed, you just use the name of your event followed by some parentheses to make the call. So why do we care about delegates and events? Well, the point is, imagine our system that we're dealing with here. We've got our scene controller, and it's just about to unload a scene. Now, it needs all of the things that care about a scene being unloaded. the things that want to save all that data, they need to actually save it. So there are two ways that you could do that. The scene controller could have a reference to every single thing that needs to save, and it could tell every single one of those things, hey, save. Or it could just say, hey, the scene is about to end. Anything that is concerned with the scene about to end, listen up and do whatever you want. So that's the way the events work. We have an event that's going to happen. Classes outside of that listen to it, and they go, oh, I care about that scene about to end, so I'm going to save my data.
They subscribe to it.
They do.
And so, I mean, just to sort of be extra clear about that point, is that you could, every time you added a new thing that wanted to happen, you could write that into your code, you could make a reference to it, you could drag the reference into the inspector, and then write the calling line where you were about to unload the scene, it calls that thing. The other is what we're doing here, it simply calls the event, and anything else that's out there that is interested can simply subscribe, can say, I want that unload event, and I'm going to plus equals myself to it. So you can load in from remotely, from anywhere in your game, you can load in interested parties, as it were. It's like if you're interested in what goes on a Twitter feed, you subscribe, you follow that person, then their Twitter comes out, you find out, but you don't, because you don't care. So the same thing is happening here, is the interested or concerned classes are subscribing to the events that they care about. And then when that event is called, they're all notified. Lambda expressions.
So this is probably the most unusual and arguably the most difficult bit of syntax we'll be covering today. So Lambda expressions don't really look like anything else in C#. And they have the syntax that you can see up there. They have the declaration of the variable names on the left, then a little arrow-like symbol, which is an equals and a greater than sign, followed by an expression or expressions as part of a function. So why do we have Lambda expressions? Well, they're generally a short way of writing functions. And since they need to be short, we want to make all of the variable names, for example, short. And something to note is that they are usually implicitly typed. So that means that you'll get something like our syntax at point 2, where it's just saying x, that's the variable I'm going to use, and then the function that I'm going to use it in, the expression that I'm going to use it in, is x is equivalent to some value. So in this case, we don't really know what x is, but we do know what some value is. So x is being implicitly typed as the same as some value. As I said, Lambda expressions are generally quite short, and they can be used to add to a delegate. So here are some examples. We've got action, my action, equals, and then open close parentheses, then the arrow, and then a debug log. So those open close parentheses, that is an example of a Lambda function with no parameters. Below that, we've got an action of type integer, which we're calling my action, and that is going to be equal to a Lambda expression where we're using x, and the expression in which we're using x is x multiplied by x. So in this case, x is being typed by the action that it's assigned to. Lambda expressions are generally used when you want a very short, very quick function that you can see all at once, because we're going to be using it to store in variables, to call within function parentheses. But on occasions, you might want a slightly longer Lambda expression. In that case, we can use braces as we would do for normal functions. So in this case, we've got our delegate, an action of type string, and we're introducing a Lambda expression to assign to that delegate. The Lambda expression has a variable called name. Then the expressions that are being used for are name to upper and print the name to the console.
The one thing that's very important to note here syntactically is that after the final closing brace, there is another semicolon. So normally when you'd write a class, there wouldn't be. In this case, it's very important that you have that last trailing semicolon.
The clue is in the title. They are expressions, and expressions always have a semicolon at the end. The main reason that we would want to use a Lambda expression is to simplify our code, because a normal function would look like this. So we've got private void sum function, string name, print name, and that's quite a lot of work for something that is very simple. Whereas if it's a Lambda expression, then it becomes very short and very succinct, and you can still tell what's happening. We can tell that that Lambda expression is just printing a name.
The scene controller script, that's sort of the background for what we're going to be using in this particular last phase. So we want to navigate to our scripts model behaviors scene control folder and open the scene controller script for editing. So we're in phase 6. We're going to go down to our scripts folder, and we're going to go down to our mono behaviors folder, and we're going to go down to scene control, and we're going to open the scene controller script for editing.
First things first, before we look into what's already written, we need another namespace. We are going to be dealing with scene management here, so we need to include the scene management namespace. So at the top, we're going to say using Unity engine dot scene management. And that's going to allow us access to classes like scene and scene manager. In our class already, we have some public events which are represented by actions. Now remember, actions are the ones that have no parameters and no return type. So we've got one called before scene unload and after scene load. So those are events that other classes are going to subscribe to, and then we will call those functions within this script. Anything that happens to be listening will get their functions called. We've got some variables set up already. We've got a public canvas group. Now remember, we had that fade image. If you remember back in the inventory phase, we looked at the fade image that covered the screen and let us fade to and from black. We have a canvas group on that, so that's going to allow us to directly affect the alpha. It also allows us to block raycasts, because when we're fading out, we don't want the player to be able to do anything. So in order to do that, we're going to block any raycasts into the scene. Next, we've got a fade duration. Obviously, that is how long it takes to go from transparent to black, and then from black to transparent. Next, we've got the starting scene name. So this is just going to be used in our start function to make sure that we load the correct scene first time. We've got another string, which is the initial starting position name. Now, we're not actually going to have any time to look into starting positions for today, but that's all set up in your scripts. And if you want to have a look at the commented version, there's some extensive comments so that you can follow along what's going on there. Next, we've got a save data variable. Now, this is something that we're going to be looking at shortly, so for now, we're not going to worry about it too much. So we've got a start function, but it's not complete yet, and we're not going to finish it off just yet. First off, we're going to write some smaller functions that we'll use as building blocks to complete the rest of this script. So the first thing that we know that our script needs to do is we know it needs to fade in and out. So we're going to create a coroutine in order to do that. So down at the bottom of your script, create a new function, which is a coroutine, so it's going to return an I enumerator. So private I enumerator, and we're going to call it fade. So we're going to use this to fade both up and down. So instead of just having one function for each, we're just going to give it a final alpha, so the alpha that we're heading towards when we're fading. So that parameter is a float, and it's called final alpha. Now, we don't want anything to happen. We don't want multiple coroutines to start if one is already happening. So we don't want anything to happen whilst we are fading. As such, we're going to create a bool to determine whether or not we are currently fading. Now, this needs to have a lifetime longer than the fade function, because obviously when we are in the fade function, we are fading. So we're going to make it as a private variable. So scroll back up to the top of your script, and create a new private bool called isFading. So this is just a flag to say whether or not we're fading currently. If we are fading, then we don't want to be able to do anything. We don't want to start any more coroutines. OK, back to the fade script. Fade function. And as soon as the fade function starts, then we know that we are currently fading. So we're going to say isFading equals true. Also, since we are fading, we don't want to allow the player to use any input. So we're going to block the raycasts, as we discussed earlier. And that is done by saying fader canvas group dot block raycasts equals true. Now, since we're doing this at the start of the function, once the fade has finished, we know the opposite is going to be true. We are no longer fading, and we don't want to block any raycasts anymore. So at the bottom of the function, we're going to say isFading equals false, and fader canvas group dot blocks raycasts equals false as well. The meat of the function is changing the current alpha of the fader canvas group. But we need to determine how fast we're going to fade. So we're going to create a float called fade speed. And what are we going to set that to? Well, what I'll do is I'll say what we're going to set it to, and I'll explain it shortly afterwards. We're going to set it to mathf.abs. And the parameter, the single parameter for that, is fader canvas group dot alpha minus final alpha. Then outside of the parentheses for that function, we're going to divide it all by fade duration. So what is that doing? Well, what it's doing is it's working out the difference between the current alpha and the alpha that we're destined towards, the final alpha, and finding the absolute value of that. We're just interested in the difference. We're not interested in whether it's positive or negative. Then we're going to divide that by the fade duration. So what we've got there is the amount of alpha that we've got to travel across and the duration that we've got to travel across it. So we've got speed equals distance over time. So we've worked out how fast we're going to change the alpha. Now we actually need to do it. And what we're going to do is we're going to use a while loop to do that. So again, I'll give you the line of code, and then we'll explain it afterwards. So it's going to be while not mathf.approximately. And then the two values in the approximately function are fader canvas group dot alpha, and the second parameter is final alpha. So what's that saying? That's saying while the current alpha is not equal to the final alpha, or it's not approximately equal to the final alpha, keep doing this while loop. So in this while loop, we actually want to change the alpha. So we're going to say fader canvas group dot alpha equals mathf dot move towards. And then we're moving from the fader canvas group dot alpha. We're moving towards the final alpha. And we're moving with a speed of fade speed multiplied by time dot delta time. So currently what's going to happen is this while loop is just going to keep getting called again and again and again and again until the alpha has changed sufficiently. We don't actually want that. What we want to do is make sure it changes over time. So within each loop, we're going to put a small delay. And we're going to do that the same way we did in the player movement script with yield return null. All that's going to do is it's going to exit the function, come back at the start of the next frame, and then repeat the while loop until the condition is no longer met. And that's our first building block. We've now got a nice contained coroutine for fading in and out. So we need to make the next building block. What's the other thing that this script definitely needs to do? Well, it needs to load a scene. But if you remember way back, we were saying that the way we want to do this is we're going to load a scene and then make sure it is the active scene, because the active scene is going to be the one that we want to unload, and that's the way we're going to tag it. So we're going to create another function, and this time we're going to create it in between our existing functions and the one we've just created. So we're sort of working from the bottom up, because we're making building blocks, and the bigger the building blocks get, the higher up they go.
So ultimately, this doesn't make a difference where in the script we're working.
Exactly.
But for our organization of our script, so that when we're looking at our script, we can understand them, so we keep the same things in the same place in all of our scripts. So these are all building blocks. We're going to be building these from the bottom up to where we are actually going to be using them.
Exactly. So this is going to be a coroutine that loads a scene and sets it as active. So we're going to come up with a really inventive name for it. So it's a private I enumerator, which we will call load scene and set active. Now, this coroutine, it needs to know which scene it is loading. So we're going to pass it a string parameter, which we'll call scene name. Now, the first thing we want to do is load a scene. And Unity allows you to do this asynchronously. So that means that it won't delay any other scripts going off. It won't stutter your game. It's going to load in the background, and then we'll come back to executing once it's finished loading. To do that, we're going to say yield return scene manager dot load scene async. So we want to load a scene asynchronously, and the scene that we want to load is determined by scene name. But that's not all. We also want to add this scene. We want to add it to the existing scenes that are already there. So this scene manager, scene controller script is going to be in the persistent scene. We want to add the security room scene to that, and we want to add the market room scene to that when we load them. So in order to do that, we're going to give it a second parameter, and that is the load scene mode, which we will use additive. Now we've loaded a scene, and we need to set it as active. But how do we know what scene that we want to set as active? Well, we need to find the scene that's most recently been loaded. So I'm going to give you a line of code again, and then we'll explain it afterwards. So it's scene, which we will call newly loaded scene. And we're going to set that equal to scene manager dot get scene at, and then within the parentheses there, we're going to say scene manager dot scene count -1. So what's going on there? Well, Unity's scene manager, it keeps track of all the scenes that are loaded. In fact, it has a collection of them, and you can find ones in the collection that are loaded by index. And they are indexed in the order that they are loaded. So the first one has an index of 0, the second one has an index of 1, etc. So given we have some scenes loaded, the most recent one is the one that is at the scene count -1. So if we've got 2 scenes loaded, the last index is going to be 1. If we've got 1 scene loaded, the last index is going to be 0.
And so that's because we're dealing with a 0-based index and a 1-based
Scene count.
scene count. Exactly.
Okay, so we found the newly loaded scene. Let's set it as active. And to do that, we say scene manager dot set active scene, and we pass it the newly loaded scene. And that's our second building block. So we're doing good. Now the next thing that we're going to make is the actual flow of the function as we change scenes. So again, we're going to go slightly further up, and we're going to create a new coroutine. So it's a private I enumerator. And this one is called fade and switch scenes, because we're going to use this to unload the scene that we're currently in and load the other scene. Now, we need to know what scene we're switching to, so we're going to give it a parameter, and that is a string which we will call scene name. Now, this is the function where we put together all our building blocks. So what do we want to happen when we click on a door and we move to another scene? Well, the first thing we want to happen is we want things to fade to black. We don't want to do anything while we can still see it. We want to fade to black, then do all the stuff behind the scenes, then fade in. So we're going to say yield return, start coroutine, and the coroutine we want to start is fade, and we need to give it an alpha. So since we're fading to black, we're going to give it an alpha of 1. We've just faded to black. We're about to unload the scene. Now is the time to call our event. So after this, we're going to say if before scene unload. Now, we're calling this without parentheses because we're just addressing the delegate. And we want to say if that is not equal to null, so if before scene unload is not equal to null, if there are some subscribers, then we will call before scene unload. So before scene unload, and then open close parentheses to actually call it. So we've just told everybody we're about to unload the scene. Now let's unload it. So scene manager dot unload scene, and then the scene that we want to unload is scene manager dot get active scene. But it's not the active scene that we want, it's the index that we want to refer it to it. So it's dot build index. Okay, so we've faded out. We've told everybody that we're about to unload the scene. We've unloaded the scene. Next, we need to load the scene. Oh, we also need to set it as active. It's almost as if we planned ahead and made a coroutine for that. So next, we're going to say yield return start coroutine. And the coroutine we want to start this time is load scene and set active. And we need to give that a scene name. Luckily, we've got one passed into the function. So we've just loaded a scene and set it as active. We have another event that we want to trigger this time, and it's after scene load. So we're going to give it exactly the same format. If after scene load is not equal to null, then after scene load, and we're going to use open close parentheses to actually call it. All right, the final thing that we need to do, we've just loaded a scene. We need to now fade back in. So the last thing in this function is yield return start coroutine. And the coroutine we're starting is fade, but this time we're fading in, so we're going to give it an alpha of 0. Okay, we're nearly there. We've nearly finished this script. We've got everything that we need to do. We need to actually have a call to it. So you may have noticed that we had a public function that is empty. that's just above the fade and switch scenes function. So we need to start the coroutine in there. However, we only want to do it if we're not already fading. So we're going to say if not is fading, then start coroutine. And the coroutine we want to start is fade and switch scenes. Now this takes a scene name as a parameter. We've got a scene reaction being passed to this. Now the scene reaction has a scene name as one of its fields, so we're going to use that. So fade and switch scenes, and then the parameter for that is scene reaction.scene name. We've just got to finish off that start function. So currently, we've loaded the persistent scene, and nothing is happening. That's because we need to actually load the first scene. So we've set the fader canvas group alpha to 1 because we want to start off with a black screen. We're not worrying about the player save data at the moment. We're going to leave that alone. So what do we want to do? Well, we want to load a scene and set it as the active scene. So instead of having yield break, we're going to have yield return and start coroutine. And the coroutine we're going to start is load scene and set active. And we need to give it the starting scene name. OK, so after we have loaded a scene and set it as active, we're going to fade back in. So we're going to start a coroutine, which and the coroutine we're going to start is fade. And since we're fading in, we want the alpha to be 0. OK, that's it.
And we're not yielding here.
We are not yielding in this last bit. That's because it's at the end of the function. So at the end of the function, we don't care whether we wait for it or not. Now, contrasting to that, if we look at the fade and switch scenes function, you'll notice that the last one, we still yield return on that one. So that is because this is a very neat and compact function that we might want to use elsewhere. And in such cases, we might want to wait for it to finish. If that is the case, then having the last fade as a yield statement means that this coroutine won't finish until the final fade has finished. So if we ever want to use this elsewhere, we can use it and wait for it to finish. However, a start function, we're never going to use that anywhere else. We're never going to wait for the start function to finish, so we don't need to have the last statement as a yield statement.
So one of the things the producer wanted us to do was to save the data when we changed our scenes. So we need to look at our save data script. So what we're going to do is navigate to the ScriptableObjects data persistence folder and open save data for editing. So we're going to go to our scripts folder. We're going to go to our ScriptableObjects folder. We're going to go to our data persistence folder, and we're going to open save data for editing. So that's save data. Open that, and then let's edit that in our script editor.
So this is a bit of a complicated one. First thing to notice is that we have the create asset menu attribute at the top of the class. And that means that we can create instances of save data from the asset menu in Unity. So save data there, you can see it at the top. We've already done that for you, so we don't need to worry about doing that. And the next thing is we've got a class within our class. So we have a nested class. And that class has been marked as serializable. So remember, serializable means that you can save that data to disk. And the class that we've marked that with is key value pair lists. So some of you may have come across the concept of key value pairs before. They're prevalent in dictionaries, which you may have used. Now, a dictionary contains two values. One of them is a key, sort of like a reference, and then the other is a value, which is the sort of the bit that you're storing compared to your reference. Now, for us, we want to use effectively a dictionary, but we only care if the dictionary has a string for its key. Also, dictionaries are not serializable, and that means we can't use a dictionary here. We need to create our own class to do the work of it. And since we're making our own class, we can make a little bit of a cut-down version. So we've got a list of keys, and we've got a list of values. Those values have a generic type. So that means we can create key value lists which have keys which are strings, and they refer to values which have a generic type. We can use them for bools, we could use them for vector 3s, etc. We haven't even put any restrictions on the type here. It could literally be anything we wanted. Now we've got a couple of functions. First off, we've got clear, and that's just going to clear both of the lists. We've got try set value and try get value. Now those are empty. We're going to have to fill those in. But let's have a look at the rest of the save data script first. So we can see we've got a whole bunch of key value pair lists, and they have different generic types. The first one's got a bool generic type, so that means it's lists of strings and bools. Next one is integers, so that's strings and integers, etc. Now these are going to be used to save information about our scene. So for example, let's say we want to save whether or not the coin game object has been turned on or off. Well, what we need is we need something to identify what we're saving. So it's going to be something like the game object activity of the coin in the market scene. Then we need to store a bool for whether or not it's on or off. So that'll be added to our key value pair lists, which have the type bool. Next, we've got our reset function. So remember, we created this resettable scriptable object class, and that is to make sure that all of our data is reset every time we run through the game. Now this will be done sort of automatically when you load and unload the game when you're making a build, but in the editor, it's not going to be done automatically. Also, if we ever wanted to run through the game multiple times in one sitting, so let's say we've opened the game, we played it a bit, and then we're going to start the game from scratch without closing it, we need to set all that data back to scratch. So that's why we're resetting it there, and that's all it's doing is just clearing all the data out of the save data scriptable objects. Next, we've got some generic functions there. We've got a save and a load function. Now, the save function is a generic function, and it takes in one of the key value pair lists, the one that matches that generic type. Now, it has a string for the key that we're trying to save, and the same generic type as a value. So this generic type, the value that we're putting into this function, is going to match the type of list that we use here. And all the function is doing is going to say lists.trySetValue, and it's going to put in the key and value as appropriate. Load is going to do something very similar. It's got the list, it's got the key, and it's got the value. The value is a reference here, and that means it works similar to the out variables that we've seen earlier. It just means this value is going to change. You can use this changed value. Now note that load is going to return a bool. So that means if we don't manage to successfully load something, we can return false. If we do manage to successfully load something, we can return true. Next, we've got a whole bunch of overloads for the functions. So overloads are when you have the same function name, but with a different signature. And all this is doing is calling the same generic version of the save function, but with the correct list already in. And that's simply a nicety. Whenever we call save, the user doesn't need to think about what it's saving, just that it wants to save a key and a value, and this will automatically sort it out. It will automatically use the correct overload, and that will use the correct function generically. OK, so our save and load functions are trying to use the try set value and try get value functions, so we need to fill those in. Let's go and do that now. The first line for our try set value function is as follows. We're going to create an integer called index, and we're going to set that equal to keys.findIndex, and then this function, we are going to pass a lambda expression. So to start off, the parameter that we're going to use in our lambda expression is x. Then we need the little arrow symbol, so that's equals greater than. Next, we're going to create an expression to actually use that x. And we're going to say x is equivalent to key. So key is the value that is a variable that has been passed into this function. So what is this function doing? Well, it is equivalent to this function. What it's doing is it's saying, get the index. That takes in a string that's a key. It's going to go through all the keys count. Once it finds one that is equal to the key value that we passed in, then return the integer for that index. If we didn't find anything, return -1. So that's quite long, but a much nicer way to write it is to have this function where we're saying, find the index where the element of the keys array x is equal to key. So here, key is being implicitly typed to a string. Now, we found the index, we're going to use it. We might have noted from the function that we just saw that if we didn't manage to find something, the index was going to be -1 or less. So we need to deal with the case where we did find something first, and that's if the index is greater than -1. So we're going to say if index greater than -1. Well, that means we found something. So what we're going to do is we're going to set the value at the same index. So we're going to say values at the index that we found, so square brackets index. And we're going to set it to the value that was passed to us. So value. So that's saying find an index where the key matches the key that's been given to us. Once you've found that index, set the values at the same index to the one that is given to us. Now, what do we do if we're trying to set a value but we can't find the equivalent key? Well, in such a case, we just want to create new keys and new values for those. So else keys.add, and the thing we're going to add to our keys array is the key. And we also want to add to the values list, so that's values.add. And we're going to add the value that we've been given. Okay, so that's that function. Let's have a go at the try-get-value function. Now this is actually going to be quite similar to the try-set-value function. We still need to find the index, and we still need to do something if we found that index. So what we're going to do is we're going to copy the first line and the if statement, but we don't need the else statement. And we're going to put that in front of our return statement. So what are we doing? Well, we're trying to find an index at a given key. If we found that, then what we're going to do is we're going to set the value that was passed to us. Remember, it's a reference variable, so we're going to swap around that equality. So instead of having values at index equals value, we're going to say value equals values at index. Now this has managed to find the value that we were looking for, so we're going to return true. But assuming we didn't manage to find the key, we didn't manage to find the correct index, then we're going to return false, which is what we've already got in that function. So we've got the scene manager that's triggering the saving and loading, and we've got our saved data that's actually storing the data, but we need a link. We need a link between the game objects that we're storing information about and the saved data. So what we've got for that is the saver script. OK, so first thing to notice, this is another abstract class. This is just a saver. We don't know what this means. We don't know what we're trying to save. So this is just the functionality that is behind saving. First off, we've got a public string called unique identifier. So remember, we're saving all our data using strings. And we need a unique way of identifying the data that we're going to save. So that's going to appear in the inspector. The designer is going to say, well, this bit of information I'm going to call exactly this. Next, we've got a public save data. So that's going to be an object reference to the save data asset that we've just looked at. After that, we've got a protected string called the key. So the unique identifier may be used by the designer to give a unique label to whatever we're saving. But we want to be more specific than that. So what we're going to do is we're going to make the key based on the unique identifier and other information. The last variable we've got is the scene controller. Obviously, we need a reference to that to know when to save and when to load. Next, let's have a look at the awake function. So in the awake function, we are looking for the scene controller. We're just doing find object of type. Then, if we've not found the scene controller, then we know we have a problem. We're not going to be able to save. We're not going to be able to load. So we better throw an exception to let the user know that something's gone wrong. Last thing to do in awake is we're going to set the value of the key. Now that is done using this abstract function setKey. The reason this is abstract is because we don't know what we're going to base the key on. That is dependent on the inheriting classes. Like if we're saving a position, the key might be different to if we're saving a rotation. It might be different to if we're saving an activity. So that is down to the inheriting class to override that function and write it. Now we've got onEnable and onDisable here, and you remember what I said? You subscribe in onEnable, and you unsubscribe in onDisable, and you're always going to be fine. You're never going to get any dangling events. You're never going to have any problems with memory leaks. Very simple, but so many people seem to get it wrong. It's really important that you must unsubscribe. So this is a really safe way of doing it. OK, we've got a couple more abstract functions at the bottom. They are save and load. Now, obviously, we don't know what we're saving and loading, so this makes no sense to have it in the saver script. We need to have it in the overriding script, in the inheriting scripts. So they are abstract. So let's have a look at a specific example of a saver. So in the same folder, we're going to open the position saver script. So we've got a position saver here. Now that inherits from saver, so it's still going to be a mono behavior just like saver was, but this time it has all of the things that we saw in saver. We have an additional variable. We've got a public transform, which is the transform that we're going to save the position of. Next, we're overriding that setKey function that we saw, and we're going to set the key to the name of the transform that we're saving. We're going to set it to the full type of a transform. So that's going to say something along the lines of UnityEngine.transform. And we're going to add on that unique identifier that the designer writes for each individual position that they want to save. Next, we've got our save function. So this is going to be called just before a scene is unloaded. And that is saveData.save. It's going to pass in the key. And obviously, it's going to pass in the position of the transform that we want to save. Next, we've got the load function. So here, what we're doing is we're creating a variable to store the position. And then we are allocating it, but only if the saveData.load function returns true. If it doesn't return true, then we're not doing anything to the position. OK. I think that's it for scripts.
So open the persistent scene. And then let's test by entering play mode.
So you can see we faded in, And if we click on the door and we change scenes, we're going to fade out and load a new scene, fade back in.
But also we can go over and collect our coin.
So now the coin game object has been turned off. If we exit the scene and then come back, theoretically, it's still gone.
Yay!
Yay.